A moonlit night.
The emergence of modern man has been closely associated with the development of the sciences. Of the many physical phenomena that men have tried to understand, few have held the fascination, or proven so elusive, as time. For at least 5,000 years, men have noted the seasons, recorded the solstices, regularly divided the year, in short, have made calendars. Measuring time with calendars is really a way of associating the Earth's rotation on its axis with its yearly revolution about the sun. As the Earth revolves around the sun, we make a sort of clock out of it. The sun is the center, the Earth is the clock hand, and the 12 hours are January, February, March, April. But as the Earth revolves around the sun, it also rotates on its axis, producing days and nights. The axial rotation of the planet and its revolution around the sun are unrelated. The Earth turns about 365 and a quarter times for every revolution, but not exactly. Men have tried for thousands of years to find some system which easily fits days into years. The search for a simple calendar has failed because the rotation and revolution are not simply related. Today, with a system of leap years and oddly divided months, we have a workable way of handling the odd relationship between the Earth's rotation and its annual journey around the sun.
What precisely is a day? Ancient Mediterranean peoples defined a day as the period between sunrises. With the invention of water clocks like this one, they were able to divide the day into smaller units. When Galileo invented a pendulum-operated clock, it was possible to prove that a day defined by successive transits of a distant star was more constant than the day based on the sun. Historically, hours, minutes, and seconds have been arbitrary divisions of a day. Now, however, short periods of time like the second can be defined independently of celestial events.
Mechanisms which tell time are usually based on some periodic motion, something that repeats itself over and over again. Electric clocks in America are driven by alternating current with a frequency of 60 cycles per second. That period of a 60th of a second is controlled by the motion of atoms in atomic clocks. Thus, the turnings of the planet no longer determine hours and seconds.
The first attempt to define the second scientifically was to take the average solar day and divide it into 86,400 equal parts. But the Earth's rotation proved too erratic to serve as a useful standard. In the 1950s, scientists studying ancient Chinese records of eclipses discovered that the lengths of days were shorter then than now. Thus men learned that gradually, as the years pass, the Earth's rotation is slowing down.
Ultimately, the Earth may slow down to a single rotation per year, so that it always keeps its face towards the sun, just as the moon now rotates to keep the same face toward the Earth. If we continued to define the second by the rotation of the Earth, seconds would grow gradually longer with every passing day. So the next refinement in the definition of the second was to measure precisely how many seconds there had been in the year 1900, and to use that as the standard second. The third and most recent refinement has been to define the second as the duration of a little over 9 billion periods of the light waves that are emitted by an atom of cesium. A clock based on this system ticks off seconds with very little error.
The principle of our cesium atomic clock is really quite simple. When cesium metal is heated, the individual atoms begin to emit light at a frequency of about 9 billion cycles per second, and those atoms are emitting a very precise frequency, more unvarying than almost anything else in the universe. We send the stream of vibrating atoms into a little chamber that's resonating at the same frequency, about 9 billion times a second. The resonating chamber interacts with the atoms inside it. It keeps the atoms vibrating, the atoms keep the chamber resonating, and the chamber controls a crystal of quartz rock, which is sending out a radio signal. In other words, the atoms control a radio signal, and the signal controls a clock.
For instance, here is a demonstration of how short a time interval is easily measurable today. We'll send an electrical pulse through about 1.5 meters of wire and see if our computing counter can measure how long it takes the pulse to travel from one end of the wire to the other. The measurement of the intervals is actually very rapid. The computer takes a moment to average them out. It takes a pulse of electricity, let's see, that's about 6,300 millionths of a second to go through the wire. People ask us why we would ever need to measure times this short, but actually, when we're considering nuclear events, 100 millionth of a second is such a long period of time that we would hardly ever talk about it. We are more concerned with time intervals in the neighborhood of a billionth of a second or shorter.
A billionth of a second is called a nanosecond. In the time it takes a firecracker to explode, 1,000,000 nanoseconds go by. In a nanosecond, a jet plane will travel about 100,000th of an inch, which is far enough for it to plow through several thousand air molecules. Inside of those air molecules, a great deal is happening in a billionth of a second. Some subatomic particles will live out their entire history. Protons in the atom's nucleus will oscillate thousands of billions of times in a nanosecond.
For a long time, men considered atoms to be the smallest parts of nature. Recently, even smaller constituents of matter have been discovered, the so-called elementary particles. Over 100 of them have been classified thus far, with names such as electrons, neutrons, K-mesons, neutrinos, and antineutrinos. The lifetime, or the decay process of these particles is extremely short, something to the order of 10 to the minus 24 seconds, which is 1 trillionth of a trillionth of a second.
In machines like this cyclotron at the University of California, atomic particles are accelerated to high velocities and studied. Physicists have recorded events taking place in quadrillionths of seconds and shorter. Some physicists believe that the evidence...
Of course, when we talk about backwards time, we're usually speaking of a rather specialized interaction among electrons, positrons, and gamma rays.
According to one model, an electron may sometimes reverse its charge and direction of spin, thus becoming a positron. In the process, it also reverses its direction in time and begins traveling toward the past. This backward journey in time may last for nanoseconds or centuries, until the particle collides with an electron and is annihilated.
It's not at all like the dramatic reversals of time found in science fiction.
Here we see a typical photograph in an elementary particle experiment. The white lines that you see here are tracks left by the particles entering a bubble chamber.
The time intervals of particle physics are so brief, they can only be measured indirectly by such methods as measuring tracks particles leave in liquid hydrogen. It takes light a trillionth of a second to cross the nucleus of a hydrogen atom, and that is also the shortest decay time of any atomic particles.
We believe that mass and energy travel in discrete bundles, or quanta, and some theoretical physicists have suggested that time also passes in discrete units. Each unit is about 10 to the minus 24th seconds. If we start with this as a unit of time and lay out 1,000 trillion of them end to end, we still have only a billionth of a second. We have an unexpected clue as to the direction of the arrow of time. It is in the concept of entropy. The persistent increase in entropy means that things tend toward a diffuse, chaotic, and disordered state. And with every passing moment, the things of the universe are becoming more disordered. The continuing increase of entropy means that an orderly little drop of ink will diffuse into 1 billion parts at the first opportunity. Increasing entropy means that the air in your room will tend toward the most disordered state possible. It will never gather together under your bed and leave you to suffocate. It means that, if left alone, every rock and every planet will slowly erode away. Everything is slowly slipping into chaos.
As time marches on, entropy marches on. Indeed, they may be more related than we imagine. Notice what happens when we make our movie violate the law of increasing entropy. When the cards go to a more ordered state, it seems that we have reversed time.
The cards jumping up violate the law of gravity, but they also violate the law of increasing entropy.
We can always tell when a movie is going backwards if it violates the law of increasing entropy. What we conceive of as time may be simply the relentless increase of entropy, of decay, of randomness. But now we are pushing the limits of what we can say of the nature of time. We simply don't know what time is. Such speculations belong properly in metaphysics and in psychology, the psychology of subjective time.
Extremely brief events are as inconceivable to us as the eons that pass on stars and planets. We are talking now of subjective time, the time that we sense. Our view of the universe is peculiarly fashioned by our lifespans. For a man whose life is less than a century, 1 billionth of a second is inconceivably brief. But if our lives happen to be as short as that of a particle called a K-meson, a second would seem a vastly long period of time.
We have talked about man's subjective view of time spans, and we have talked about the measurable intervals of physics. But now we aren't talking about anything. Or rather, what we're talking about now is now. What is now? How long is now? Is now a psychological idea? Is it a notion in physics? When it's now on Earth, is it now throughout the galaxy?
The idea of now assumes simultaneous moments throughout the universe. But in physics, events which are simultaneous for one observer may not be simultaneous for another. In other words, now is not a meaningful term in physics.
Psychologically, there is a continually moving point in time which we call now. This now separates the past from the future. It is always now. Time is a long string of nows which stops abruptly at the present. Looking back on them, we see these nows as instants in time and as points in our movement through space.
So far, we have suggested that time, as defined in physics, moves forward uniformly, unchanging throughout the universe. Yet we know that our personal sensation of the duration of time intervals is affected by circumstances. Presumably to an insect whose life is brief and whose movements are rapid, our activities are slow and lumbering. Relative size affects our subjective perception of time. But we are now going to suggest that there are conditions under which the measurable rate of time changes. Physicists have now proven that the duration of an interval is related to the velocity at which a thing is moving through space. For example, a clock ticking off seconds on a very distant star, moving very rapidly away from the Earth, would seem to us to take hours or even months between ticks. This notion of time slowing down, or time dilation, was first suggested by Albert Einstein. His ideas radically changed our view of fundamental physics.
Yes, I'm on up, Mr. Whoa, whoa. Slow speed,
Many concepts in physics are first posed as thought problems. A famous thought problem is the twin paradox. It involves two brothers. One is going to a distant star and will return. As the astronaut is accelerating away from the Earth, that is, his velocity is continually increasing, he notices that clocks on Earth are going faster than his clock. However, as he approaches 99% at the speed of light, he stops accelerating. He is going at an unchanging velocity. But what is this? Clocks on Earth are no longer going faster than his clock. In fact, They're going slower. The spacecraft slows down to go around the planet. Since his speed is again changing, he observes that clocks on Earth are again going faster than his clock. Now he is returning home. He has had a dazzling trip, time seeming to slip back and forth. What will the Earth be like when he gets back? He is 12 years older. His brother, however, has grown into an old man. The world is no longer interested in his little experiment.
Here, at the 2-mile-long Stanford University Accelerator, experiments have been performed which conclusively prove that under certain circumstances, time can be caused to slow down.
We have a problem. In this stainless steel tube directly above me, we're sending pi mesons produced by our accelerator into the bubble chamber. These pi mesons are very, very short-lived particles. In fact, they only live about 26 billionths of a second. In that amount of time, you could only expect them to go about 27 feet before decaying, even if they were going at the speed of light. Now, on the other hand, our bubble chamber is located 250 feet downstream of where I'm standing. The question then is, how do the particles live long enough to go into the chamber? The answer is relativity. We're standing on the 82-inch bubble chamber at the Stanford Linear Accelerator Center, and right now, pi mesons are going into the chamber at the rate of 30 per second, 15 each time you hear the noise in the background. Now, the pi mesons are traveling so fast, in fact, at over 500 million miles per hour, that in their space-time frame, length appears to be contracted, and to us, time appears to be dilated. Now, what do I mean by that? Well, the 400-foot distance through which the pi mesons have to travel in order to get to the chamber looks to a pi meson as if it is only about 4 feet long, which is quite a difference. Also, in terms of length of time dilation effect, time is slowed down as we observe it by a factor of over 100, so that instead of living only 26 billionths of a second, the pi meson lives long enough to travel 2,700 feet before it ultimately decays. This is quite a bit longer of a distance than the 400 feet that we've been talking about.
Thus, in actual controlled experiments, physicists have shown that time is variable with regard to velocity. The same equations that showed how mass may be transformed into energy in a nuclear reaction showed that objects traveling at different velocities exist in different time frames.
The great, shifting, mutable universe which Einstein revealed necessitated redefining our most basic notions: energy, mass, space, gravity, and time.
Gradually, we learned to predict physical events, to describe operations mathematically. But our definitions are strictly operational. As with length and mass, the other basic physical concepts which we use operationally but can't define, time can also be used and measured. But finally, we find it impossible to answer that most compelling question: what is time?
There's no use trying, Alice said. One can't believe impossible things.
I dare say you haven't had much practice, said the Queen. When I was your age, I always did it for half an hour a day. Why, sometimes I've believed as many as 6 impossible things before breakfast.